Lunarcrete, also known as mooncrete, an idea first proposed by Larry A. Beyer of the University of Pittsburgh in 1985, is a hypothetical aggregate building material, similar to concrete, formed from lunar regolith, that would reduce the construction costs of building on the moon. Only comparatively small amounts of moon rock have been transported to Earth, so in 1988 researchers at the University of North Dakota proposed simulating the construction of such a material by using lignite coal ash. Other researchers have used the subsequently developed lunar regolith simulant materials, such as JSC1, developed in 1994 and as used by Tatanji et al. Some small-scale testing, with actual regolith, has been performed in laboratories. However, the basic ingredients for Lunarcrete would be the same as those for terrestrial concrete: aggregate, water, and cement. In the case of Lunarcrete, the aggregate would be lunar regolith. The cement would be manufactured by beneficiating lunar rock that had a high calcium content. Water would either be supplied from off the moon, or by combining oxygen with hydrogen produced from lunar soil. Lean et al. Used 40 g of the lunar regolith samples obtained by Apollo 16 to produce Lunarcrete in 1986. The Lunarcrete was cured by using steam on a dry aggregate/cement mixture. Lean proposed that the water for such steam could be produced by mixing hydrogen with lunar ilmenite at 800 degrees Celsius to produce titanium oxide, iron, and water. It was capable of withstanding compressive pressures of 75 MPa, and lost only 20% of that strength after repeated exposure to vacuum. In 2008, Sam Tatanji, of the University of Alabama in Huntsville, and Richard Grogel, of the Marshall Space Flight Center, used a lunar soil simulant to determine whether Lunarcrete could be made without water, using sulfur, obtainable from lunar dust, as the binding agent. The process to create this sulfur concrete required heating the sulfur to 130 to 140 degrees Celsius. After exposure to 50 cycles of temperature changes, from -27 degrees Celsius to room temperature, the simulant Lunarcrete was found to be capable of withstanding compressive pressures of 17 MPa, which Tatanji and Grugel believed could be raised to 20 MPa if the material were reinforced with silica, also obtainable from lunar dust. There would need to be significant infrastructure in place before industrial-scale production of Lunarcrete could be possible. The casting of Lunarcrete would require a pressurized environment, because attempting to cast in a vacuum would simply result in the water sublimating, and the Lunarcrete failing to harden. Two solutions to this problem have been proposed: pre-mixing the aggregate in the cement and then using a steam injection process to add the water, or the use of a pressurized concrete fabrication plant that produces precast concrete blocks. Lunarcrete shares the same lack of tensile strength as terrestrial concrete. One suggested lunar equivalent tensioning material for creating pre-stressed concrete is lunar glass, also formed from regolith, much as fiberglass is already sometimes used as a terrestrial concrete reinforcement material. Another tensioning material, suggested by David Bennett, is Kevlar, imported from Earth, which would be cheaper, in terms of mass, to import from Earth than conventional steel. This proposal is based on the observation that water is likely to be a precious commodity on the moon. Also, sulfur gains strength in a very short time and doesn't need any period of cooling, unlike hydraulic cement. This would reduce the time that human astronauts would need to be exposed to the surface lunar environment. Sulfur is present on the moon in the form of the mineral troilite, FeS, and could be reduced to obtain sulfur. It also doesn't require the ultra-high temperatures needed for extraction of cementitious components, e.g. anorthosites. Sulfur concrete is an established construction material. Strictly speaking, it isn't a concrete as there is little by way of chemical reaction. Instead, the sulfur acts as a thermoplastic material binding with a non-reactive substrate. Cement and water are not required. The concrete doesn't have to be cured. Instead, it is simply heated to above the melting point of sulfur, 140 degrees Celsius, and after cooling it reaches high strength immediately. The best mixture for tensile and compressive strength is 65% JSC1 lunar regolith simulant and 35% sulfur, with an average compressive strength of 33.8 MPa and tensile strength of 3.7 MPa. Addition of 2% metal fiber increased the compressive strength to 43.0 MPa. Addition of silica also increases the strength of the concrete. This sulfur concrete could be of a special value for dust minimization, for instance to create a launching pad for rockets leaving the moon. It provides less protection from cosmic radiation, so walls would need to be thicker than concrete walls. The water in concrete is an especially good absorber of cosmic radiation. Sulfur melts at 115.2 degrees Celsius, and lunar temperatures in high latitudes can reach 123 Celsius at midday. In addition, the temperature changes could change the volume of the sulfur concrete due to polymorphic transitions in the sulfur. See allotropes of sulfur. So unprotected sulfur concrete on the Moon, if directly exposed to the surface temperatures, would need to be limited to higher latitudes or shaded locations with maximum temperatures less than 96 degrees Celsius and monthly variations not exceeding 114 degrees Celsius. The material would degrade through repeated temperature cycles, but the effects are likely to be less extreme on the Moon due to the slowness of the monthly temperature cycle. The outer few millimeters may be damaged through sputtering from impact of high-energy particles from the solar wind and solar flares. This may, however, be easy to repair by reheating or recoating the surface layers in order to sinter away cracks and heal the damage. David Bennett, of the British Cement Association, argues that Lunarcrete has the following advantages as a construction material for lunar bases. Lunarcrete production would require less energy than lunar production of steel, aluminium, or brick. It is unaffected by temperature variations of plus 120 degrees C to 150 degrees C. It will absorb gamma rays. Material integrity is not affected by prolonged exposure to vacuum. Although free water will evaporate from the material, the water that is chemically bound as a result of the curing process will not, he observes, however, that Lunarcrete is not an airtight material, and to make it airtight would require the application of an epoxy coating to the interior of any Lunarcrete structure. Bennett suggests that hypothetical lunar buildings made of Lunarcrete would most likely use a low-grade concrete block for interior compartments and rooms, and a high-grade dense silica particle cement-based concrete for exterior skins. In situ resource utilization, astronautical use of materials harvested in space.